Representation Theory of Finite Groups, Lecture 21, Viennot's Geometric Construction. Let us start by briefly recalling what we did in the recent lectures. So we defined the so-called insertion algorithm, where we can insert a new positive integer b in a standard generalized Young tableau of the row shape, where we have the elements a1, a2, and so on ak written in the natural order. So this goes as follows. If b is greater than ak, then we just append b at the end of the row and issue the global stop sign. If b is smaller than ak, then we pick the minimal index I such that b is smaller than ai, and we replace ai by b in our row, and the output is this new row together with the number ai. One usually says that b bumps ai from the row. Taking this into account, we can define the insertion of a new positive integer b into a standard generalized Young tableau T. So we try to insert b in the first row from the top using the previous algorithm. So if the outcome reads stop, then we stop. Otherwise, the algorithm changes the first row and gives us a new number which was bumped from that row. Let's call it c. So then we insert c in the second row. If we get stop, then we stop. Otherwise, the second row is changed and a new number d is bumped out of the second row. And we continue down the rows until we get the stop sign. So using this insertion algorithm, we can define the so-called Robinson-Schensted correspondence. Let sigma be an element in Sn which sends 1 to a1, 2 to a2, and so on. Define the tableaus p0 of sigma and q0 of sigma as the empty tableaus. For each I from 1 to n, we define recursively the insertion tableau pi of sigma as the tableau which we obtain from pi minus 1 of sigma by inserting the number ai. And we define the recording tableau qi of sigma by adding the box with the number I in it to qi minus 1 of sigma at the same position at which a new box is added in pi of sigma relative to pi minus 1 of sigma. So we denote by rs of sigma the pair pn of sigma and qn of sigma. And for lambda a partition of n, we have the set syt lambda of all standard Young tableaus of shape lambda. Then the Robinson-Schensted correspondence says that the map Rs, which starts from a permutation, an element in Sn, and which produces a pair of standard Young tableaus of the same shape, and this shape is a partition of n. So this map is a bijection between Sn and the set of pairs of standard Young tableaus of the same shape, and this shape should be a partition of n. So the aim for today is we will provide a geometric construction for the pair Pn of sigma and Qn of sigma. So the construction which uses basic geometry of the Euclidean plane. So the starting point of this construction is the graph of sigma in a plane. So our running example will be the following sigma, which is a permutation of 8 elements, so which sends 1 to 3, 2 to 8, 3 to 1, 4 to 2, 5 to 4, 6 to 7, 7 to 5, and 8 to 6. So this sigma has the following graph. So we have our plane. So the horizontal line gives us the coordinates of the starting point, and the vertical line gives us the coordinates of the images. So in particular, sigma sends 1 to 3. So 1 is sent to 3, 2 is sent to 8, 3 to 1, 4 to 2, 5 to 4, 6 to 7, 7 to 5, and 8 to 6. So this is our graph of sigma. So we will give a geometric construction for the Robinson-Schensted correspondent of sigma, and in order to be able to compare it with our running example, let us compute the Robinson-Schensted correspondent for our sigma which is 381, 247, 5, 6, using the one-line notation. So we start from the empty tableau, and then we insert 3. So the insertion tableau is 3, the recording tableau is 1. Then we insert 8, this 8. 8 is greater than 3, so it goes to the first row. So we get 3, 8, and 1, 2. Next we insert 1. 1 bumps 3, so 3 goes to the second row. So we have 1, 8, and 3 as the insertion tableau, and 1, 2, and 3 as the recording tableau. Next we insert 2. 2 bumps 8 from the first row, but 8 is greater than 3, so it goes into the second row. So we have 1, 2, and 3, 8 as the insertion tableau, and 1, 2, and 3, 4 as the recording tableau. Next we insert 4. 4 is greater than 2, so it goes into the first row. So the running insertion tableau is 1, 2, 4, 3, 8, and the recording tableau is 1, 2, 5, 3, 4. Next we insert 7. Again, 7 is greater than 4, so it goes into the first row. So the insertion tableau will become 1, 2, 4, 7, and 3, 8, and the recording tableau is 1, 2, 5, 6, and 3, 4. Next we insert 5. 5 bumps 7 from the first row, 7 bumps 8 from the second row, and 8 goes into the third row. So we get 1, 2, 4, 5, 3, 7, and 8 as the insertion tableau, and 1, 2, 5, 6, 3, 4, and 7 as the recording tableau. Finally, we insert 6. 6 is greater than 5, so it just goes into the first row. And we get the answer. So the insertion tableau for sigma is 1, 2, 4, 5, 6, the first row, 3, 7, and 8. So the shape is 5, 2, 1. And the recording tableau for sigma is 1, 2, 5, 6, 8, 3, 4, and 7. So the geometric construction of the Robinson-Schensted correspondence is based on the notion of a shadow of a point. So if we have a point in the plane, its shadow is the following region. So we start from the point, we draw the horizontal ray to the right and the vertical ray upwards, and the area in the northeast between these two rays is called the shadow of this point. So the shadow of a permutation sigma is defined as the union of all the shadows of all points of the graph of sigma. So here is our running example. So here we have 8 points in the graph of sigma, and we take the union of all shadows, and we get this gray region in our picture. So the first main notion related to the shadows is the first shadow line. The first shadow line is defined as a boundary of the shadow of sigma. So in our running example, so here we have this gray region, which is the shadow of our sigma, and the shadow line is given here as a red line. So it's a vertical ray with the horizontal coordinate 1 going down to the point 1, 3. Then we have the horizontal segment between 1, 3 and 3, 3. Then the vertical segment between 3, 3 and 3, 1. And then the horizontal ray from 3, 1 all the way to the right horizontally. So the second shadow line of sigma is defined as follows. We take the graph of sigma and remove from it all the points which belong to the first shadow line. Then we take the shadow of the remaining points, and the second shadow line is the boundary of that region. So here is our running example. So we start from the graph of sigma, and we remove the points 1, 3 and 3, 1, which belong to the first shadow line. And we take the shadows of all other points. And then the boundary of this, which is given by the violet in the second picture, is the second shadow line. And further shadow lines are defined recursively. So to define the third shadow line, we take away points on the first and the second shadow lines, take the shadow of what is left, and the boundary is the third shadow line, and so on. So in particular, in our running example, we will have 5 shadow lines, which can be seen at this picture. So we have the red shadow line, which is the first one, so it contains points 1, 3 and 3, 1 of our graph. So the second shadow line is the violet shadow line. It contains the points 2, 8 and 4, 2 of our graph. The third shadow line is orange. It contains the point 5, 4 of our graph. Then the fourth shadow line is teal. It contains the point 6, 7 and the point 7, 5 of our graph. And finally, we have the blue shadow line number 5, which contains the point 8, 6 of our graph. So let us record the horizontal coordinates of the vertical rays of these shadow lines. So the first shadow line has the horizontal coordinate of the vertical ray equal to 1. So for the second shadow line, it's 2. For the third shadow line, it's 5. And then we have 6 and 8. And also we record the vertical coordinates of the horizontal rays of our shadow lines. 1, 2, 4, 5, and 6. And now we have to compare these two rays, 1, 2, 5, 6, 8, and 1, 2, 4, 5, and 6, with the Robinson-Schensted correspondent of sigma. So if we look at our Robinson-Schensted correspondent of sigma, we see that 1, 2, 5, 6, 8 is the first row of Qn, and 1, 2, 4, 5, 6 is the first row of Pn. So these coordinates of the rays for the shadow lines, they agree with the first rows in the Robinson-Schensted correspondence of sigma, at least in our running example. So let us formulate it as the general statement. Proposition: the horizontal coordinates of the vertical rays of the shadow lines give the first row of Qn of sigma of the recording tableau. And then the vertical coordinates of the horizontal rays of the shadow lines, they give the first row of the insertion tableau Pn of sigma. In order to prove this proposition, we make the following observation. Lemma: assume that the vertical line x is equal to k intersects exactly I shadow lines. Let y1, y2, and so on yi be the vertical coordinates of the lowest points of these intersections. Then the top row of pi of sigma is exactly y1, y2, and so on yi. We prove this lemma by induction on I. The basis I is equal to 1 is obvious. It follows directly from the definitions. And for the induction step, we just check the changing from x is equal to k to x is equal to k plus y. By construction, the shadow diagram reflects the bumping procedure. So let us illustrate how this works on our running example. So recall our insertion tableaus pi sigma for our running example sigma. So we start from the empty tableau, then we have the tableau 3, then the row 3, 8, then 1, 8, and 3, 1, 2, and 3, 8, 1, 2, 4, and 3, 8, 1, 2, 4, 7, and 3, 8, then 1, 2, 4, 5, and 3, 7, and 8, and finally 1, 2, 4, 5, 6, 3, 7, and 8. So let us now look at our shadow diagram for our sigma and look at the intersections of the shadow diagram with the numbers x is equal to k. So here is the shadow diagram, and the vertical line x is equal to 1. It's slightly shifted. It's x is equal to 1, 1 in order to be able to see clearer the intersection points. This line intersects only the first shadow line, and the intersection is 3. So we have exactly this 3 as in the first insertion tableau. So now we move to x is equal to 2. It intersects the first shadow line also at point 3, but it also intersects the second shadow line, and the lowest intersection point is 8. So the second insertion tableau is one row consisting of 3 and 8. Now we take x is equal to 3. When we try to insert the point 3, 1, so this is the third insertion, we insert 1. This is smaller than 3, so it bumps 3. So it gives us this corner in the shadow line, and we get now 2 points of the intersection. With the first shadow line, we intersected the coordinate 1, and with the second shadow line, still in the coordinate 8. So we have 1 and 8 as a third insertion tableau. We move to x is equal to 4. There we try to insert 2. 2 is greater than 1, but it's smaller than 8. So 2 will bump 8, which gives us this corner. And so in the second shadow line, the intersection coordinate changes from 8, which we had, to 2. So now we have 2 intersections and coordinates are 1 and 2. This gives us this 1, 2 in the first row. On the next step, we take x is equal to 5. We have intersection with 3 shadow lines, and the points are 1, 2, and 4, because we have a new shadow line which corresponds to inserting 4. Next step, x is equal to 6. We insert 7. This gives us a new shadow line because 7 is bigger than all other intersection points. And so we keep all previous intersection points, 1, 2, and 4, and get a new intersection point with shadow line number 4, which is 7. Next step, x is equal to 7. We insert 5, which bumps 7. So we get this corner, and the last intersection point changes the coordinate from 7 to 5. So we have intersections at the coordinates 1, 2, 4, and 5. And finally, we insert 6 and look at the vertical line x is equal to 8. So 6 is greater than all previous intersection points, so we just get one new intersection point with this new shadow line at the coordinate 6. And our final read is 1, 2, 4, 5, and 6, exactly as the first row of P8 of sigma. So let us now prove the proposition. So the claim about Pn of sigma follows directly from the previous lemma, which we explained. So let us now prove the claim for Qn of sigma. Let us note that the tableau Qn of sigma contains a box with a number k at the position j in the first row, if and only if sigma of k is greater than every element in the first row of pk minus 1 of sigma. So this follows directly from Schensted's insertion algorithm. By the previous lemma, we see that this happens if and only if the line x is equal to k intersects the shadow line number j in a vertical ray. And this implies exactly the claim. So this gives us a geometric construction for the first row in the Robinson-Schensted correspondent of sigma, both for the insertion and the recording tableaus. But how do we proceed with other rows? In order to do this, we need to look at northeast corners of the shadow diagram. So we are done with the first row, and we want to determine the second row. So we look at the northeast corners of the shadow diagram. So here are the northeast corners of our running example, which are marked by small black squares. So here we have a northeast corner on the first shadow line, here we have one northeast corner on the second shadow line, and here we have a northeast corner on the fourth shadow line. So these northeast corners, they correspond exactly to the bumpings. So this northeast corner records the information that when inserting the number 1 on the third step, it bumps the number 3, which was in the first position, staying there from step number 1. So this northeast corner records the information that when at the fourth step we inserted number 2, it bumped number 8, which was in the first row at the second position since step number 2. And similarly, this northeast corner records the information that inserting 5 at the 7th step, this 5 bumped the number 7, which was staying at 4th position from the previous step. So now we can define the second skeleton of our shadow diagram, and this is simply the shadow diagram for the northeast corners of the original shadow diagram. So we had 3 northeast corners, the points 3, 3, 4, 8, and 7, 7. And we take the shadow diagrams for these points. We get 2 shadow lines, one containing 3, 3, and the other one containing 4, 8, and 7, 7. So let us record that the horizontal coordinates of the vertical rays of these 2 shadow lines are 3 and 4, and the vertical coordinates of the horizontal rays of these 2 shadow lines are 3 and 7. And these coincide exactly with the second rows in Qn of sigma and in Pn of sigma, respectively. And to go with further rows, we just do the same procedure again, recursively. So to determine the third row in both Pn of sigma and Qn of sigma, we look at the northeast corners of the second skeleton shadow diagram. So in our running example, we have only one northeast corner in the second skeleton, and this is a point 7, 8. And then we take the shadow diagram for the northeast corners of the second skeleton, and this will be the third skeleton shadow diagram. And in our running example, it consists only of one shadow line, which has this point 7, 8. And in this shadow line, the horizontal coordinate of the vertical ray, unique vertical ray, is 7, and the vertical coordinate of the horizontal ray is 8. And we again observe that this agrees with the third row in Qn of sigma and respectively with the third row in Pn of sigma. So in general, we define the ice skeleton as a set of northeast corners of the shadow lines in the I-1st skeleton, and the eye level of the shadow lines as the shadow lines for the ice skeleton of sigma. And the general statement, the main result for today, is the following theorem. So the ice row of Qn of sigma coincides with the horizontal coordinates of the vertical rays of the ice level shadow lines. And the ice row of Pn of sigma coincides with the vertical coordinates of the horizontal rays of the ice level shadow lines. The proof proceeds by induction on I. So the basis, this is for the first row, this we have already proved. And for the induction step, one just notes that the construction of northeast corners explicitly records the information provided by the bumping procedure in Schensted insertion algorithm. So this proves this theorem. This theorem has some interesting consequences. The first of them is the following corollary, which is due to Schützenberger. Let sigma be an element in Sn, and let the Robinson-Schensted correspondent of sigma be the pair P of sigma and Q of sigma. Then, the Robinson-Schensted correspondent of sigma inverse is the pair Q of sigma, P of sigma. Proof. We note that the graph of sigma inverse is obtained from the graph of sigma by reflecting with respect to the line x is equal to y in our coordinate plane. Hence, the skeletons for sigma inverse are obtained from the corresponding skeletons for sigma by reflecting with respect to the same line x is equal to y. And now the claim follows simply from our main theorem by noting that when we reflect with respect to x is equal to y, then horizontal and vertical coordinates interchange. So the Robinson-Schensted correspondent for sigma inverse is obtained from the Robinson-Schensted correspondent for sigma by swapping the two tableaus. Another corollary, let sigma be an element in Sn such that the Robinson-Schensted correspondent of sigma is equal to P of sigma and Q of sigma. Then sigma is an involution in the sense that sigma square is equal to the identity if and only if P of sigma is equal to Q of sigma. Proof: this follows from the previous corollary, since the condition that sigma square is equal to the identity is equivalent to the condition that sigma is equal to sigma inverse. Here is an example. Recall that we previously computed the Robinson-Schensted correspondence for all elements in S3. So here we recall the outcomes, and the involutions are emphasized by magenta color. So the Robinson-Schensted correspondent of the identity is the pair 1 to 3, 1 to 3. So the same tableau of shape 3. And of course we see that both tableaus are equal. So this is an involution, and P of it is equal to Q of it. Next, the Robinson-Schensted correspondent of 2, 1, 3. This is also an involution, and the image consists of the pair of the same tableau of shape 2, 1. We have 1, 3 in the first row and 2 in the second row. So the third element, we take 1, 3, 2. This is again an involution, and its image has the same tableau repeated, shape 2, 1, and 1, 2 in the first row and 3 in the second row. So the next element is 3 to 1. This is again an involution, and the image consists of two tableaus of shape 1, 1, 1, and it's a unique tableau 1, 2, and 3. Then we have the element 2, 3, 1. This is not an involution, and the insertion tableau for it is 1, 3, and 2, and the recording tableau is 1, 2, and 3. And finally we have the elements 3, 1, 2. It has the insertion tableau 1, 2, and 3, and the recording tableau 1, 3, and 2. So we see that for involutions, the Robinson-Schensted correspondence consists of repeating the same tableau. And these are exactly the involutions which have this property. So let us finish with some problems and questions. Question number 1. Compute the Robinson-Schensted correspondent for the permutation 732 for 165 in S7 using Viennot's geometric construction. Question 2. Use Viennot's geometric construction to determine sigma in S5, whose Robinson-Schensted correspondent is a pair of the following tableaus of shape 3, 2. So the first tableau is 1, 3, 4, and 2, 5, and the second tableau is 1, 2, 5, and 3, 4. Question 3. Use Viennot's geometric construction to determine the unique involution sigma in S6, whose insertion tableau is the tableau of shape 3 to 1, with 1 to 5 in the first row, 3, 4 in the second row, and 6 in the third row. Question 4. Write down all details in the proof of the mate theorem. And question 5. Show that there is a bijection between the set of all involutions in Sn and the set of all standard Young tableaus with n boxes. Thank you very much, and see you next time.